Hello and welcome to a new problem solving session. Uh, we need to find out magnetic field again, and this time the problem at the screen simply says that compare the magnitude of magnetic fields B naught at the center of the circular current loop and B at a point in the plane of the circular current, a distance r from the center of the circle, for a small r much greater than capital R, that is the radius of the circular loop itself. We know many things like according to the Biot-Savart law, the magnetic field of a closed conductor carrying a direct current of magnitude I can be obtained by dividing the conductor into small pieces and summing the contributions of each piece. We can calculate easily the magnetic field at the center of the circular loop, and that is quite easy basically to calculate. And I know you can calculate it, and you must have calculated it, and its value is simply mu naught I by 2r. And sometime the similar way, you have sometimes calculated that magnetic induction at any point on the symmetry axis that is perpendicular to the plane of the circular loop at a distance r from the center of the circle along the axis. And I remember you must have got the magnitude of this magnetic field as mu naught I r square by 2 a small r square plus r square raised to 3 by 2. But this is not the induction measured in the plane of the circular current involved in this problem. In this problem, we need to calculate the magnitude of magnetic field at a point in the plane of the circular current, and that is a different kind of problem, but we can find it as well. And it looks something like I have already a picture and a plan how I think to solve this problem. And so let's start solving. And let's start from the fact that magnetic field created by a closed plane conductor is equal to the field of a point-like magnetic dipole far from the conductor. And the strength of this dipole, this is called magnetic dipole moment, is product of the current in the conductor and the area bounded by the conductor. Therefore, if we replace the circular current by a different shape, more convenient to handle, I say. The area of which is like this. And that means the area of which is the same as that of the original circular current, that was pi r square, and the strength of the current in it is also the same, so that of the circular current in the problem. Then their magnetic fields will be same, at least far from this conductor at the far point we needed to find. Things will be approximately same. Hopefully same impact. So consider a small circular conductor that we have in the picture and calculate its magnetic field at this point P. And according to the Biot-Savart law, the section D and FC do not contribute to the magnetic field at point P, simply because mu naught I by 4 pi dl cross I, dl and r are parallel. That means dl cross r vanishes, and the contribution of the other two arcs we have is, if you want to calculate this, you will have something like magnetic field equals mu naught I upon 4 pi dl. Just consider this element as dl, any small element at it anywhere as dl. Then you can simply write as dl by r square. dl cross r here, the angle between dl and r is going to be 90 degrees, so you can write here simply as dl cross r by r cube in place of dl cross r by r cube as dl by r square minus, because both of them, this thing and this thing, are going to produce different magnitude of magnetic field. So for this part we are again going to consider it as a small part of it as dl, but the distance from point P will be something like r plus d, and put a square here and try to calculate this integration. And you can use this angle phi for this, and you are going to get the result simply as mu naught I upon 4 pi. The first term, every dl is at the same distance from point P, so you can take this r square out and you can write dl as simply as r phi. In terms of this phi or psi, whatever it is, or psi it is perhaps, I would like to write it phi, r phi by r square. A minus second term will be simply r plus d phi divided by r plus d square, and this will be approximately equal to mu naught I by 4 pi phi d by r square. And let's now use the fact that area of this, a small circle or whatever, a small arc, must be the same as the area of the circle given in the problem. So we have area of this small part simply as, we can write d multiplied by r phi, and this will be equal to r square pi. This must be or pi r square, and from here we can get easily the magnitude of magnetic field simply as mu naught I r square by 4 r cube. And now you can compare your results, and the problem is solved, I think. So thank you very much for watching.